Since there are no restriction on which terminal voltages and the currents should be considered independent variable or dependent variable, so we can generate many parameters, and that shows that there are different combination of dependent and independent variable we can have for two-port network. For example, in impedance parameter, we have V1 and V2 to be our dependent variables, and our I1 and I2 to be the independent variable. And for admittance, reverse is the case. We have I1 and I2 to be our dependent variables, and our V1 and V2 to be the independent variables. And for hybrid parameter, just like we said in a little while ago, we have our V1 and I2 to be the dependent variable, and our I1 and V2 to be the independent variables. And for inverse hybrid parameter, which we just finished with, we have our I1 and V2 to be our dependent variables, and our independent variables are the V1 and I2. So that makes us to have different alternatives as to analyzing or treating or solving two-port network because of these different combinations. So another type of another set of parameter which we'll be considering is transmission parameter, also known as ABCD parameter, in which we have our V1 and our I1, the input voltage and the input current, to be our dependent variables, and our V2 and I2 to be our independent variables. So our transmission or ABCD parameters are one of the parameters of two-port network to analyze the two-port network, and the formula is V1 equals to A V2 minus B I2, and our I1 equals to C V2 minus D I2. In matrix form, we have a V1 I1 2 by 1 matrix equals to A B C D 2 by 2 matrix multiplied by our V2 minus I2 2 by 1 matrix. And in short form, we have our matrix T multiplied by our V2 multiplied by our minus I2. So we could see that our input variable V1 and I1, they are the dependent variable, and our output variable V2 and minus I2, those are the independent variable. We should also notice that in computing the transmission parameter, minus I2 is used instead of I2. We have the negative I2 because the current is considered to be leaving the network, as we will see in slide 19. So in this diagram, we can see that our I2 minus I2, the direction is flowing out of the network, unlike what we had in admittance and impedance parameter, in which our current is flowing, our I2 is flowing into what we call the black box, but in this case it's flowing negative, is flowing outside. So, and this is done merely for conventional reasons. When you cascade two ports, that is the output to input, it is logical to think that your I2 is leaving, and is used in power industry also to consider our output current to be leaving the two ports. Now in the two equation in slide 18, that is our V1 equals to A V2 minus B I2, and our I1 equals to C V2 minus D I2. In those two equations in slide 18, those two equations provide a measure of how the circuit, two-port network or two-port circuit, transmits voltage and current from the source to the load. The application of transmission parameters. They are used in analysis of transmission lines such as cable and optic fiber. The cables are used in the transmission cable for power line, distribution of power networks, and then optical fiber in the telecommunication industry used to carry voice and data. And the reason why they are useful in this transmission line is because they express the sending, they show the sending end variables in terms of the receiving end variables. That is the input voltage and input current in terms of the output voltage and output current. So they are called the transmission variable because they are used in transmitting these variables. They are also used in the design of telephone systems, microwave network, and radar system. Also, they are useful in cascade network, very useful in the cascade network. From the formula of transmission parameters stated in slide 18, from V1 equals to A V2 minus B I2 and I1 equals to C V2 minus D I2. From these two formulas, we have our open circuit voltage ratio, that is our A, will be equals to input voltage over output voltage, provided our output current equals to 0. And our B, that will be our negative short circuit transfer impedance. Our B will be minus V1 over I2, provided our V2 equals to 0. And our C, which is open circuit transfer admittance, will be input current over output voltage, provided that our output current equals to 0. And our D is equals to minus I1 over I2, provided our V2 equals to 0, and that is called a negative short circuit current ratio. So we can see, because our A and D are ratios, they are dimensionless. They don't have dimension because the A is a voltage ratio, is just like a voltage gain. So if we say that, if we use a normal mathematics, the voltage and the units will cancel out, and also for D. So A and D are dimensionless, and our B is in ohms, as we can see, is an impedance, and our C is in Siemens. Note that the transmission parameter is also reciprocal if A multiplied by D minus B multiplied by C equals to 1. If your AD minus BC equals to 1. This is just a simple mathematics. Remember, I can say my AD is also equals to 1 plus BC, and I can as well say my BC equals to AD minus 1. And I can also manipulate it further and say my D equals to 1 plus BC over A. Note